Anytime we're dealing with numbers, we need to pay attention to significant figures. So this is a worksheet that I've put together that gives some examples for common cases of significant digits. I'm going to be posting this to the Moodle as a PDF, but I'm also going to post this as a video and kind of go through all the rules in case you're feeling a little bit unfamiliar with them. So the first thing we need to pay attention to are zeros. All digits are significant unless you have zeros at the beginning of the number. An example of zeros at the beginning of the number would be in this number right here. These 3 zeros before the 3 are all placeholder zeros. Over here in this other example, all 5 of these zeros are placeholder zeros. Those zeros are not significant, but all of the other digits in the number are significant. So all digits are significant except zeros at the beginning of a number. If we have terminal zeros to the right of a decimal or also inside a number, these numbers are significant as well. Those zeros can be significant. An example of a terminal zero to the right of a decimal would be in this number. These 2 zeros before the 9 are not significant, but the terminal 0 here at the right of the number is significant because there are digits that are non-zero to the left. Anytime we have a 0 in the middle of a number, surrounded by non-zero digits, these numbers are always significant too. There are some situations where you will encounter a number with terminal zeros to the right that doesn't have a decimal, and in this case, we have some ambiguity happening. An example would be something like 500 here. I don't have any decimal places and I don't have any non-zero numbers to indicate to me whether or not for sure these ones are significant. This number could theoretically have either 1, 2, or 3 significant digits, and so if you have an exact looking number like this, where we have zeros for our multiple digits here, then make sure that you use scientific notation. So if you wanted to write 500 with 3 significant digits, we could either write that 5.00 times 10 to the 2, or we could write 500 with a decimal place right here at the right, indicating that those 2 numbers to the left of the decimal were also significant. If I wanted to write 500 and indicate that I only had 1 significant digit, then I should write 5 times 10 to the 2. Or if I had 2 significant digits, 5.0 times 10 to the 2. We really can do pretty much anything we want with scientific notation, and I generally recommend that you use scientific notation to avoid ambiguity. For example, up here in this example 2, when I have 0.00346, one of the ways that you know that these leading zeros are not significant is if you were writing this number in scientific notation, you would write 3.46 times 10 to the minus 3. So notice that those 2 leading zeros after the decimal place and also the one to the left of the decimal, they all disappear when you write this number in scientific notation. So this is one of the ways that you can know that some numbers are significant or aren't, is to try writing them in scientific notation. Now I know all of you have used significant digits in calculations, and I'm just going to go through our 2 main examples of significant digit types when we are doing mathematical calculations. So our 2 classifications are for multiplication and division and for addition and subtraction. And I usually find that the multiplication division one is the one most people remember. This is the one where you look at all of your numbers that are being multiplied together, and in your final answer, you just keep the smallest number in any of these individual numbers. So for example here, my first number has 3 significant digits, my second one has 6, and my third one has 4. So my final answer, I'm going to keep 3 significant digits and round everything else off. In addition and subtraction, we still are paying attention to the least number of significant digits, but when we add and subtract, we're paying attention to the decimal places specifically. These are the places that tell us about the precision with which that number was measured, and that's why with addition and subtraction, those decimal places are the ones that are important. So in this first number, I've got 2, then 5, then 3, then 1 decimal place. So in my final answer, I can only keep 1 decimal place. Now, we have a couple of special cases that I'm going to go through as well, and one of these is with exact numbers. Exact numbers are either numbers that you count. For example, I might count that there are 22 students in my classroom, And that's an exact number. I know it with absolute certainty. There is no, I can count all of you in my classroom, and there is no like partial person or anything like that. There's no rounding off of people. So those are exact numbers. Anything we can count are exact numbers, and they have infinite certainty with them. The other thing that has exact numbers or lots of decimal places are generally constants, like the gas constant, the Planck's constant, speed of light. All of these tend to have a lot of significant digits with them. Other numbers are things like pi and e. Those ones are irrational numbers, and they have an infinite number of significant digits as well. So never allow those numbers to limit the number of significant digits in your answer. So I'm going to go through two examples here. One of them is a situation where I have 6 coins. Each of them weighs 5.43 grams, and I want to know what the total mass is. So if I'm going to do this in my calculator, I'm going to just multiply 6 times 5.43, and that feels like multiplication. But because 6 is an exact number, what I'm effectively doing is I'm adding 5.43 6 times. And since each of those has 2 decimal places, I'm going to keep 2 decimal places in my answer rather than go with this number has 3 sig figs, and therefore I'm going to round to 3 sig figs. I'm still going to use the addition rule even if it looks like multiplication when I have this exact number. So another situation here is calculating the area of a circle. So the area is 2 pi r squared, or excuse me, just pi r squared. And so my radius, 2.445 meters, is multiplied by itself. So I'm going to use multiplication rules, and I'm not going to worry about pi because that has infinite numbers of significant digits. So my radius has 4 sig figs, and I'm going to keep 4 sig figs in my final answer. Another special case is when we have log calculations. And for chemists, this comes up most often when we're calculating pH. So any kind of log calculation, when we look at the log number, for example, pH is a log number. And that means it's scaled on the log base 10 scale. And if you need a refresher on that, I'm going to refer you to other places. I'm not going to go through it right here. But the short version is that this 2 in front of the 0.71, this is a placeholder that tells us what power of 10 we're in. So 2.71 as a pH really only has 2 significant digits. It's the 7 and the 1 that came from the actual concentration. So when we go backwards and we calculate what the concentration of that would be by taking 10 to the minus pH, we can only keep 2 significant digits for that concentration. And if we do that math, we'll get 1.9 times 10 to the minus 3. So our final answer has 2 significant digits, just like our pH. So we're going to do another example here because pH is always complicated, just to give us extra practice. Here's an example of us calculating the pH of a 3.24 times 10 to the minus 5 molar solution. So I'm going to go I'm just going to assume this is the concentration of the proton since I didn't specify. So with my log, I've got minus log of that concentration, and when I put that into my calculator, I get 4.489. This number has 3 significant digits. The number to the left of the decimal in pH is a placeholder, and so the 489 make up my 3 significant digits for my answer. Now, anytime we're doing a calculation and we're paying attention to significant digits, we're going to end up rounding things off. And most of you, I think, are already perfectly familiar with rounding, and I'm just going to go through it really quickly here because there's 1 or 2 special cases. So generally, if we have a number that's less than 5 that we're going to be rounding off, then we just round down. And if we have a number that's greater than 5, we're going to round up. And so in this case of an example A and example B, my number 5.49145 is going to be rounded to 4 significant digits. And so these 4 digits are the ones that I'm going to keep. So I look at that next number there. I see that it's a 4, which is less than 5. So I just round down to 5.491. Now, in a slightly different scenario, instead I have 5.49165. And so if I'm still rounding to 4 significant digits, I'm going to look at that number and say, okay, that number is above 5. I'm going to round it up to 5.492. Now, the special case that we have here is when we are rounding and we have exactly 5 as the last digit that we are rounding off. So this number, 4.996, I want to round it to 4 significant digits, and I'm going to keep it at 4.996 exactly, because our final digit that we're keeping is even, and the number that we are rounding away is exactly 5. This is one of those special cases. If we have exactly 5 as our final answer, then we're going to keep our last digit even. So if that means that we had a 5, like it was 4.9955, then I would round up to 4.996 to make it even. If I have an even number as the number next to the 5 that's in question, then I'm going to just keep it even. So this comes up very rarely because we almost never have exactly 5 at the end of a number, but I just wanted to mention it. Anytime you have multiple calculations, then retain all the digits until you get to the final answer, and then look at all the steps in your calculation and decide how many significant digits you get to keep from each step, and then use that to figure out how many final significant digits you have.